Okay, dear students, the next chapter is chapter 4, and in that we are going to look at this Markov inequality. Which is a very easy to understand, both the proof and geometrically to understand. So let first explain in terms of geometry. Let us consider a graph given to us. So a graph is given to us. Consider this is the graph f, and what is also given to us is this is integrable. Now consider any constant c, and then look at the points where the function overshoots this c value. Okay. So what do I mean by that? So this is the constant c. I look at all those points where f of x is bigger than or equal to c, and hence you can see that the underlying portion will be this. Okay. So this and this together is what we call it as, let's say, e suffix c to be set up of x in the space x such that your f of x is bigger than or equal to c. And right now I took a positive function. If you want to consider a general real valued function, then it should be modulus of f of x. Okay. So call this set E of c, and what this theorem says is that if you look at measure of this EC, so measure of this EC is less than or equal to 1 by c times the norm of the function. Okay, that's the statement says, but look at the picture and then we'll try to understand. So this is my set EC, and now suppose if I ask the following information: mu of EC, and I multiply with the constant c. Okay, then can you see that it is actually this part? This is the underline, and it is clear that this is less than or equal to integration of the function on the full space. So the picture that I have written is in terms of Riemann integration, but the statement says that even it works for though the function is continuous and other things, this works even for Lebesgue integration. So hope you understood. So look at the green statement that I have given here. If you take the c to the other side, this is what it tells you, and the right hand side, this information is given by, this is same as same integral f dv. Okay, since I took the f to be positive, it's the case, and if I take f to be a real valued map, then you will get this. There will be modulus of f of x, and here also you can see modulus of f of x. And the graph may be below, but it will be bounded in between those two information. Now let's go through the proof, which are the easy proof. So let's start with what is the measure of EC, and we know this by definition it is nothing but integration of a characteristic function of this set EC with respect to the Lagrange measure. See, as long as this mu is measurable, this is the definition over the full space X. But I know that that's also equivalent to integrating the constant function on this set. This is by definition that we have learned yesterday. Now all that we need to observe is that using the information that C is strictly positive, I can write this as well as multiply but by my choice on easy, my f of x is bigger than or equal to C. Just note down. So this information tells you my f of x is bigger than or equal to C, and hence we get just the monotonicity of, but again this EC is actually subset of the original space X, and this is what we call it as L1 norm of the function f. So all it says, the Markov inequality says that if I look at the points where the function is bigger than or equal to C, and if I multiply with the C, that will be less than or equal to norm f. So it gives some kind of lower bound for the norm of the function f.